Hello, this is Sushruth, and I'll detail our investigations into what happens inside recurrent neural networks as they perform object categorization. So, recurrent connections can increase the efficiency of neural networks trained for object recognition. In 2017, while faced with the challenging task of finding an intact object within a lot of clutter, it was shown that recurrent neural networks can do quite well. They outperform parameter matched feed-forward networks. This was an exciting result, and we were very curious as to what is happening inside such RNNs which are trained to do object recognition in cluttered images. Specifically, what kind of information is actually being used in the recurrent neural network to improve the category inference iteratively. So you have the feed-forward sweep, some information is extracted there, and that information is used through via the recurrent connectivity, the top-down and lateral connections, to impact the next step. What is this information, and what kind of operations are happening, what kind of interactions are happening between the recurrent flow and the feed-forward information flow. So what we proposed was category inference, which is done iteratively in a recurrent neural network, could use information which was category orthogonal. For example, let's say you have this image where the network has to say the target is 5. So there are two generative variables for the object. You have the category and the location. So what we thought could happen is the feed-forward sweep could extract information about the category and the location of the intact object, and then using evidence from on the location dimension, the network could constrain where it wants information from for the next iteration. So it could use information from this location dimension and say perform spatial attention using feedback, and then in the next step it only receives input from this small part, and its category information would improve. Also its location information inference would improve because the debris has been filtered. So how can we find if this is exactly what is happening in a recurrent neural network trained on um, object recognition in cluttered images? So given this formalism, we propose three signatures that we can look for. One, category and auxiliary variable information should increase through time because the category inference is improving and it requires improved auxiliary variable information. And we probably might be able to say debris filtering and also auxiliary variables could actually be shown to affect category inference through recurrence. This could be done with a perturbation analysis, which I don't go into too much detail in this presentation, but you can look at the paper for more details. So the recurrent neural network we used was simple. It had two convolutional layers and a fully connected layer with a dense top-down and lateral connectivity matrix. Crucially, we also sent top-down connections to the input because we wanted to see if debris filtering actually happens. This network was trained to do only object categorization, irrespective of all the other information that may be present in the image. So our images comprised of a lot of clutter and one intact digit or object. So we had 20 categories, the 10 digits from MNIST and 20 objects from Fashion MNIST, and these objects could move over the image, so that's the auxiliary variable of location. The objects could be tilted or not, that's the auxiliary variable of orientation, and then the objects could be small or big, that's the auxiliary variable of scale. So these are category orthogonal variables, and we wanted to see if these impact category inference. So the first thing we wanted to see is can we check if there is information about category and auxiliary variables in the network. So we trained support vector machines to quantify information. So in this case, if you want to know if there's category information, you train a 20-way SVM on each time step at each layer. So what we saw is for each layer across time steps, category inference increases. This is just a signature of iterative category inference. Correspondingly, we also find increase in information about all the three auxiliary variables through time. So this confirms the first signature that information about category and auxiliary variables increases through time. So the network is actually extracting these auxiliary variables, which are category orthogonal and not task relevant from our standpoint. We also check the inputs, and the modulated inputs, the input plus the top-down connection information flow, shows signatures for iterative clutter reduction. So as we go deeper into the network in terms of time, the debris is reduced and the network only retains, the input only retains information about the intact digit. to know if the auxiliary variable information is actually sent through the recurrent flow through top-down and lateral connections, and that is actually impacting category inference. We did a perturbation analysis, which is quite cool. You should check it out in the paper. In the interest of time, I cannot present it here, but spoiler alert, signature 3 was also confirmed. Auxiliary variables are indeed used in the recurrent computations. Given these results, we can conclude that category inference in recurrent neural networks can be enhanced using category orthogonal generative factors of the images. The cool part is you don't need to actually train the network to use these category orthogonal parts. It actually creates its own implicit goal to perform categorization. We think that this ability might be present in all neural networks. It doesn't have to be a recurrent neural network. And this has actually been shown in deep feed-forward neural networks that you can find auxiliary variable in those networks too, auxiliary variable information in those networks too. However, we think recurrent neural networks might have an advantage because they have an inductive bias for conditional computations, and our proposal included a conditional computation. So it might be the case that RNNs can learn these kinds of like extracting auxiliary variables, this kind of processes, extracting auxiliary variables and using them to constrain category inference better than a feed-forward neural net. And that might be why people report higher efficiency for RNNs as compared to other architectures. Please ask me a question if you want to know more, or you can look at the paper. Thank you.